Okay, I want to go ahead and take a look at a couple more quick examples of working on the central limit theorem questions involving a single mean here. So let's take a look at this problem. The amount of time that a drive-through bank teller spends on a customer is a random variable with a mean of 6.3 minutes and a standard deviation of 3.2 minutes. If a random sample of 64 customers is observed, 64 customers, find the probability that their mean time at the teller's window is, okay, then we got three questions, parts A, B, and C. All right, so this is about their mean time. This is a question on X bar. This is a question on X bar, their sample mean, okay? We have a sample of n equals 64 customers, so we can answer probability questions about the mean using the central limit theorem. Okay? So recall that X bar, it's going to set some of this up on the side here, right? X bar with a large enough sample size is approximately a normal distribution, all right? And it's going to have a mean that is equal to the population mean, which in this case is 6.3. 6.3. And we're given the population standard deviation is 3.2. And remember that the standard deviation of X bar, sigma of X bar, according to the central limit theorem, right, is equal to sigma over the square root of n. Sigma over the square root of n. So in this case, we're looking at 3.2 divided by the square root of n, divided by the square root of 64. Well, we have n is 64 here. Square root of 64 then is 8. So 3.2 divided by 8, and I've got that. That's actually a nice 0.4. So this has a mean of 6.3, and it has a standard deviation. Our standard deviation is 0.4. Let's remember that this is our standard deviation, not our variance here, right? So this is our mean. We have our mean here. And in this case, we've notated our standard deviation. All right. So now this is just a normal distribution question, right? We've applied the central limit theorem. We have our mean. We have a standard deviation here. Now these are just central limit or standard normal distribution questions that we need to convert to. So their mean time is at most 5.7 minutes for part A. That would be the probability then that X bar is greater than, no, what is at most 5.7 going to be? Let's interpret this. At most 5.7 would be less than or equal to 5.7 minutes. Less than or equal to 5.7. So we can convert this to a standard normal distribution question here. Subtract the mean of the distribution for X bar here now is 6.3. Divide by its standard deviation, which is 0.4. And so this should be the probability then that a standard normal random variable z is less than or equal to, I've got my calculator next to me to do 5.7 minus 6.3. That's negative 0.6 divided by the 0.4 then is negative 1.5. Standard normal random variable z is less than negative 1.5. Let's go ahead and take a look at our normal table for that. Negative 1.5. Negative 1.50 is right here. That is 0.0668. 0.0668. That'd be at most 5.7. Okay, good, cool. Part B, more than 7.1 minutes. So the probability then that X bar is more than 7.1, that would be greater than 7.1 here, greater than 7.1. And these greater than questions, we can use the normal table to do that, but we're going to want to look at the complement here. So we'll do 1 minus the probability, because remember the normal table gives us less than or equal to probabilities, those cumulative ones. So we're going to do 1 minus the probability that X bar is less than or equal to 7.1. And so now we're going to convert this to another standard normal question. So 1 minus the probability that z is less than or equal to 7.1 minus the mean, which is 6.3, divided by the standard deviation, which is 0.4. So we have 1 minus the probability Got my calculator ready to go. 7.1 minus 6.3 is 0.8 divided by 0.4. That is 2. That is 2. 1 minus probability that z is less than or equal to 2. Oh, that's about 97%, but let's double check here. Where's 2? We're going to need to go to the positive side of the normal table. 2.0 is 97.72%. 0.9772 right there. 0.9772. We want 1 minus that though, right? 1 minus 0.9772 is equal to 0.0228. 0.0228. And part C, at least 6.3 minutes, but less than 6.7. So we're talking about the sample, we're talking about the mean here, x bar. At least 6.3 minutes. So x bar should be at least 6.3, so greater than or equal to 6.3, but less than or equal to 6.7. 6.7. All right. So we have probability in between bounds here, so we'll go ahead, convert to a standard normal probability, and then we can look at using our normal table to find the desired area. So we're going to go ahead and let's see here. At least 6.3. So 6.3, so we subtract the mean on the left and then divide by the standard deviation on the left. Standard normal here. And then less than 6.7, so we have 6.7 minus the mean, which is minus 6.3, divided by 0.4. And I guess I should be careful here, because technically speaking, you've got to watch, well, it's good to be detailed. At least 6.3 would include 6.3. Less than 6.7, this is actually a strict inequality, but because we're talking about continuous random variables here, whether or not I include 6.7 or not, isn't actually going to change the desired probability. If this was a discrete problem, you know, we might have to be more detailed there. But because this is continuous, it doesn't matter if we include 6.7 or not at this point. Let's simplify what we have inside here. 6.3 minus 6.3, that is 0 on the left. So we have a 0 less than or equal to z. And then 6.7 minus 6.3, well, that's just 0.4. Divided by 0.4, these are some really nice numbers here. Probability that a standard random variable z is between 0 and 1. Between 0 and 1. Remember, we can always draw a picture to help figure out what this area is that we want. But we want, ideally, well, the way I would do this is I would take the probability, all the probability, that is that z is less than or equal to 1, and subtract the probability that we don't want. We don't want the probability where z is less than or equal to 0. The 0 value, actually, hopefully we know what that is without having to look it up, right? That is the standard normal random variable right in the middle at the mean. That is 50%. What we just need to look up is the probability that z is less than or equal to 1. So there's some probability there, minus 0.50. So what's the probability that z is less than or equal to 1? Go ahead and look over here. 1.0, 1 standard deviation to the right. That is 0.8413. 0.8413. And so minus 0.5, and we see that the probability that we are looking for then is 0.3413, or 34.13%. And that is how we can work through those. Again, so much of this really relied on us just setting up the sample, or setting up the distribution of x bar, right? The mean of x bar is equal to the mean of the population, according to the central limit theorem, and then the standard deviation of x bar is sigma over square root of n. Once you have that, then these become ordinary area under the normal curve questions. All right. Now, central limit theorem, like we've mentioned many times, the special thing about it is it applies to so many scenarios. And so let's take a look at this example here. This one is a bit of a different type of problem that we haven't quite seen yet, but we'll see how we can apply the central limit theorem here. We have a discrete distribution x. X takes on the values 6, 7, 8, and 9, and the probabilities that it does that is 0.2, 0.4, 0.3, and 0.1. Okay. Notice these probabilities sum to 1, right? 0.2 plus 0.4 is 0.6. Plus 0.3, that's 0.9. And then you add the 0.1 there, you get a 1.0. So we're going to do a few things in this problem before we apply the central limit theorem. Let's start by just finding the mean and variance of x. All right, so this is just an old, ordinary, discrete probability distribution. Let's go ahead and find the mean of our random variable x. So the mean of x here, or mu, remember that's just the expected value of x. That's just the expected value of x. This is in the discrete case, so this is going to be equal to 6 times 0.2 plus 7 times 0.4 plus 8 times 0.3 plus 9 times 0.1. And so let's go ahead and run that through a calculator. Times 0.2 plus 7 times 0.4 plus 8 times 0.3 plus 9 times 0.1. And so we have a mean of 7.3. We have a mean of 7.3. How do we find the variance of x here, right? How do we find the variance of x? This is not the sample variance. This is the variance of the random variable x. Okay. And sometimes you don't remember the exact formula, but you do know that there is something that exists. So don't feel bad if you ever want to pop back to your notes here and say, okay, well, where do we talk about variance of random variables? That is in chapter 4 here. So what do we know about the variance of a random variable? Here's the definition of variance, sigma squared. It's the expectation of the squared deviations from the mean, x minus mu squared. That's the expected value of that. We also have an alternative result, one that I prefer to use. Theorem 4.2 at the bottom here. This is how I would compute the variance. Sigma squared is the expected value of x squared minus mu squared. So let's go ahead and use that. Reference theorem 4.2. Back to our task at hand. So we have the expected value of x. To find the variance, we're going to need the expected value of x squared. Expected value of x squared. So this is a similar computation, but you're just going to square all of your x values. So we'll have 6 squared times 0.2 plus 7 squared times 0.4 plus 8 squared times 0.3 plus 9 squared times 0.1. Remember, you don't square the probabilities, you just square the x values. And so I'm going to run that through a calculator here. So 36 times 0.2. And then 49 times 0.4. And then 64 times 0.3. And then 81 times 0.1. Boom, this is 54.1. That's not the variance, that's just the expected value of x squared, right? So remember then that sigma squared is equal to 54.1 minus 7.3 squared. So 54.1 minus 7.3 squared is a variance of 0.81. So we have a mean of 7.3 and a variance of 0.81 for a random variable x. Okay. So part B, here's where our stuff starts coming into play. Find the mean and variance of x bar when you have a random sample of size 36. So we have n equals 36. We have n equals 36. This is a large enough sample size. Central limit theorem certainly should apply here for the sample mean x bar. All right, well, we know that the mean of x bar should be equal to the mean of the random variable, which is going to be 7.3. And the variance, sigma squared, of x bar is equal to, according to the central limit theorem, sigma squared over n. So in this case, we have sigma squared as 0.81. N is equal to 36, so it's 0.81 over 36. And if I want to get that as a decimal, that's 0.0225. That would be the variance of our sample mean, 0.0225. So what are we going to do here? We're going to apply this result to answer this question. What's the probability that the sample mean, we must be assuming that we have the same sample size of 36, so we're talking about that sample, is less than 7.4? Okay, well, here we go. Now this just becomes a typical normal distribution type problem, right? Because we know that x bar is going to be approximately normal with a mean of 7.3 and a variance of 0.0225. So this is equal to the probability that a standard normal random variable z is less than 7.4 minus the mean, which is 7.3, divided by the standard deviation. Remember, this is the variance, so the standard deviation would be the square root of 0.0225. There we go. There we go. I'll point out one detail here too before we finish out this computation, is in case you're thinking about, hold on, Aaron, x is discrete. X is discrete. Don't we need to do some sort of continuity correction on this? No, we do not. Why not? Well, this is not about x. This is about the sample mean x bar, right? The sample mean x bar is not a discrete random variable. The mean is continuous, right? The sample mean x bar can take on any value, any real number essentially, right? So this is not approximating a discrete problem here. The sample mean is continuous, and so we don't need to do a continuity correction. So what do we have when we do 7.4 minus 7.3, and then we're going to do divided by the square root of 0.0225. That means z is less than, I've got 0.66 repeating. 0.66 repeating here. Okay, so we're going to go ahead and take a look at this in the normal table. 0.66. Here is 0.6. Here is 0.66 right here. So we could take that, or this would be 0.67, or some average value in between there would be okay. I would accept either of those on anything written coming my way. So I'm gonna go ahead and write this as 0.747. Let's see. I'm gonna do 745. Well, 0.66 repeating is almost directly halfway in between here, right? So what's the average of those two values? What if we do 0.7486 and I go plus 0.7454 and then I divide by 2? 7.747. I'm going to go ahead and report that. 0.747. So this is approximately equal to 0.747, and I'll report it like that, right? Because 0.666, this is almost halfway between, 0.66 and 0.67. So take the average of those values is relatively reasonable as well. Or either one's just fine, okay? But we're looking at about 74% or about 75%, more or less.